Have you ever stopped to think about how the heater way at the bottom of an oven manages to cook your food so evenly? Or what about an air conditioner? How does that one box on the wall cool down an entire room? Well, the answer to both is this invisible force all around us called convection. And in this explainer, we are going to crack the code of how it works. It all starts with one simple question, right? This is the mystery we're here to solve. I mean, why is the AC always stuck way up high near the ceiling? It might seem totally random, but I promise you, it's based on a fundamental rule of physics. And by the end of this, you'll see the logic perfectly. But before we can solve that puzzle, we need to get our hands on the single, powerful rule that governs pretty much everything here. Once you get this one rule, you'll start seeing it everywhere. This right here, this is the key. This is our mission for today. Everything, and I mean everything, comes down to understanding how density changes in a fluid, like air or water. If we can nail this one concept, we can unlock the entire puzzle of convection. So let's break it down. Okay, so what actually happens when you heat up a fluid? First off, the amount of stuff, the mass, it stays exactly the same. You're not adding or removing particles. But those particles get energized. They start zipping around and spreading out, which means the volume increases. And here is the absolute crucial part. If you have the same amount of stuff in a bigger space, well, it's less packed together. Its density goes down. To put it simply, density is just how tightly packed something is. And in fluids, less dense things always want to rise above more dense things. It's the reason a big log floats on water or why oil floats on top of vinegar in salad dressing. That simple principle, well, that's the engine for everything we're about to see. And all of that leads us right here to what I call the golden rule of convection. It's a really simple three-step process. Step 1, a fluid gets heated. Step 2, it expands and becomes less dense. And step 3, because it's less dense, it rises. Heat, expand, rise. Remember that. That simple pattern is what drives this whole process. Okay, we have our rule. Now let's put it to the test. First up, our first case file, the electric oven. So here's the puzzle, right? The heating element is at the very bottom. So how on earth does it cook the pizza on the top rack? Think back to our golden rule. What has to be happening to the air right there above that heater? So here's the dynamic in action. The hot air, it follows our rule perfectly. It expands, becomes less dense, and it starts to rise. But at the exact same time, the cooler air that's already at the top is the complete opposite. It's more dense, so it naturally wants to sink. You can probably see the cycle that's about to form here, can't you? And there's our cycle. The air near the heater gets hot and rises, just like our rule says. But it has to go somewhere, right? So it pushes that cooler, denser air at the top out of the way, forcing it to sink downwards. That cooler drops, reaches the heater, gets hot itself, and the whole process starts all over again. This constant circulation is called a convection current, and it's exactly what makes sure your entire oven heats up nice and evenly. Okay, one case down. Now let's apply that exact same logic to our original mystery. Case file, the air conditioner. All right, time to solve it. We know that hot, less dense air rises, but an air conditioner does the opposite. It makes air cold. So knowing what you know now, what do you think that cold air does? It's the same principle, just running in reverse. The AC cools the air around it, making it contract and become denser. This heavy, cool air naturally sinks down towards the floor. And as it fills up the bottom of the room, it pushes the lighter, warmer air up towards the ceiling. That warm air then gets sucked into the AC, gets cooled, becomes dense, and the cycle continues. So the reason the AC is high on the wall is to let gravity do all the work of circulating that nice, cool air for you. Genius! So we've seen how convection works with heating from below and cooling from above, but what happens when the situation is a little more complicated? Our final case file is a real test of our understanding, the hot water puzzle. This one's a real head-scratcher. In most hot water tanks, the heating element isn't at the very bottom. It's actually partway up. So it heats the water around it, which then rises and creates a convection current to warm all the water above it. But this creates a really strange puzzle. Why does the water below the heater stay so cold? And this reveals a key limitation. Our golden rule says heated fluids become less dense and rise. It says nothing about them sinking. The convection current only moves heat upwards from the source. It simply has no way to carry heat down. It's a one-way street. Now, You might be thinking, well, shouldn't the heat just kind of spread downwards on its own? And that's a good question. But it turns out that water is actually a really bad conductor of heat. So without that convection current to physically move the hot water around, the heat just stays trapped in the top part of the tank. Okay, let's make this practical. Let's say you're an engineer and you need to make sure all the water in that tank is at least 65 degrees Celsius. You have to place a temperature sensor at either position X, near the bottom, or position Y, near the top. To be safe, where do you put it? X or Y? The only safe place is position X, down at the bottom. And why is that? Because the bottom is always going to be the coldest part of the tank. A sensor up at Y could read a perfect 65 degrees, while the water down at X is still lukewarm. So by putting the sensor at the coldest spot, you absolutely guarantee that when it finally hits 65 degrees, every single drop of water above it is even hotter. We've seen the rule, we've solved the case files. Now let's look at one final, really simple experiment that makes this entire principle of density crystal clear. This little experiment makes the whole process visible, and it shows us exactly why density is the key that unlocks everything about convection. Okay, picture this. You take a flask of hot, red-colored water, and you carefully place it right on top of a flask of cold, clear water. You might expect them to mix all up, right? But they don't. The hot water just sits there. And why? Because it's less dense, and it's already on top. The denser cold water is perfectly happy to stay at the bottom. They're stable. This proves it. Without a density difference driving the movement, nothing happens. Density is the engine. So let's go all the way back to our original goal. It was all about explaining convection using density changes. And now you can totally do that. You know that heating a fluid makes it less dense, so it rises. And you know cooling a fluid makes it more dense, so it sinks. That simple up and down movement is the heart of it all. Mastery achieved. So you've cracked the code of convection in ovens, rooms, and water heaters. The final thought I want to leave you with is this. Where else is this powerful force at work? Think bigger. I'm talking about the massive convection currents in our oceans, or the ones in our atmosphere that create our weather. The very same simple rule we learned today is literally shaping our entire world. Thanks for joining me on The Explainer.